cartography and output maps look like in the form of using zeros and ones, so using binary code to generate maps itself. And this is very primitive style maps. This is the first upper left-hand corner is looking at York County houses. We can see that on the left-hand side, we have latitude. On the bottom, we have longitude. And we have individual points that are representing features such as houses. We can also see in the bottom right-hand corner, using zeros, we can see annual rainfall in inches. Again, this is just an example of early types of maps. So when we look at the programs that were used early on for map production, these were early sequence programs that helped define the code behind the map itself. Okay, so using DOS and Unix, where we were using prominently command line style programming skill sets. Now, we are seeing this pendulum switch where it became more user-friendly, and now we have buttons and graphical interfaces for users, but you can still code and write script on the back end on the GIS side of things. So in looking at the brief history of GIS was significantly altered by the personal computer, allowing for folks to bring work home, that computer small enough that can fit on a desk with large processing power. So during the 1980s, the new GIS software moved from these large computers to this more desktop interface. We also saw in the early 1990s, this kind of programmer's world shifted into a more graphical user interface known as a GUI, so that we saw developments that improved the user interface and the kind of user level friendliness, the user experience with these softwares. And now we're seeing these new developments where we have this strong integration of the global positioning systems, our GPS data, that can plug right into our software systems that provide us almost real-time information, dynamic maps. And, these GPS data collection systems can be in the form of a chip that's in your Nike shoe, can be in the form of a wristband that you're wearing when you're going on jogs. So it's pretty impressive the change that's happened over a relatively short period of time in this industry. We also see that with the use of satellite imagery, with the use of drones or unmanned aerial vehicles, we're able to obtain high resolution imagery as a base layer at a relatively low cost. And then the whole game changer took place when we started to integrate the internet-based real-time data collection and web-based GIS maps. So we also are starting to see a humanitarian effort for projects that take place where we have open data for emergency purposes. Now, you guys may have heard of a program called OpenStreetMap. OpenStreetMap is a online mapping interface that allows for you as a community of data and collection to input information such as a hiking trail or any information that you would see based on what you're interested in. Well, during natural disasters, OpenStreetMap turns their whole focus into providing the best data they can to create the most updated maps for rescue workers. So a project that my class was involved in back at the University of Nevada, Reno, was really one of the first time that open source OpenStreetMap was used to help update maps for Haiti. And so I'll provide this link for you. It's just a 2-minute YouTube video that talks about what the class was doing and how they were working on it. So when we look at remote sensing is defined as a collection of data about an object from a distance. Okay, and so remote sensing takes the form of an orbital platform, satellite. You can be collecting information from satellites. You can be collecting information from airplanes. You can be collecting information from helicopters. And on those platforms, you're going to have different types of sensors based on the information that you're collecting. And so, for example, you may have a visible light, near infrared, and different wavelengths depending upon the type of information that you want to collect. So the role of remote sensing as a source of GIS data. So it provides us perspective of biological, physical, and human factors at local, regional, and global scales. So it's relatively fast and inexpensive compared to sending people out in the field to do field surveys, and especially at a coarser scale. And it allows us access to remote or restricted areas. So this is going to be something that's key, that really allows us to analyze areas of the globe that we may not get to. It also allows us to monitor and establish frequent and systematic measuring techniques from satellites. And the great thing about this, about remote sensing, is that it's repeatable. So we can have repeatable imagery that takes place so that we can monitor something such as a glacial movement that takes place over a series of time. And this really fits into the scientific method in that it is repeatable and it can be done over and over again. Okay, so when we talk about remote sensing, we're going to go ahead and I'm going to introduce to you the electromagnetic spectrum. This is going to be important for the different types of wavelengths and type of information that we are collecting. We will talk about this later on in the semester, but I want to talk about shortwave radiation. So when we talk about shortwave radiation, we're talking about energy that is emitted as we define as being hot. So for example, the sun itself is a great example. With its surface about 6,000 degrees Celsius, emits short wavelengths. And so in this whole electromagnetic spectrum, short wavelengths are often defined as being very harmful. Okay, so these are made up of our gamma rays, our X-rays, and our ultraviolet rays. And these wavelengths are measured in the nanometers in size. We can see on this chart itself, the size of the waves are much smaller from crest to crest or trough to trough. Now, again, these are the most harmful rays that we see within the electromagnetic spectrum. And as I mentioned, these are going to be our gamma radiation, our X-rays, our ultraviolet, some of our invisible light, and near infrared. And so we know that hot objects emit much more radiation than cooler objects. So as we go into our long wave radiation, these are going to be emitted by cooler objects. So for example, the sun's energy heats up the Earth's surface. As the surface heats up, it emits long wave radiation back. It's much cooler than the sun, so it emits a longer wavelength as a whole. And the average temperature of the Earth's surface is 16 degrees Celsius, so much cooler in retrospect to the sun's surface. So these are going to be the longer waves. If we look at our wave chart at the bottom here, these are waves that are measured in meters, centimeters and meters in length. So these are much longer as opposed to the nanometers that we saw. And these are made up of our microwaves, radar, infrared, TV, and radio. Okay, so we can look at our electromagnetic spectrum from a whole, and we can see going from the shorter wavelength side, the gamma rays, to the longer waves that we identified as being much longer from crest to crest and trough to trough. Okay, so when we talk about sensors, now these sensors are measuring different wavelengths, okay? And it really depends upon why that information is being collected and what is going to be, how is it going to be used, and what information they're trying to obtain from it. And that's really going to determine the different types of wavelengths that you're going to be collecting. So two different types of sensors to know about. We have passive sensors, which radiation is received at the sensor and it originally comes from an external source. Okay, so this is passive. So an example, we have a sensor that's attached to a satellite, and the radiation received at the sensor is coming from an external source, and that light is the sun. Okay, so here's some examples of satellites that use passive sensors: Landsat, MODIS, Iconos, and QuickBird. Okay, so again, if you were to look at a Landsat imagery for 10 o'clock at night over the Western Hemisphere, because this passive sensor depends upon an external source for the light, we're going to see a very dark image, okay? Because at that period of time, we know that it is dark. The sun is not a key player. The next type of sensor is active, where energy is generated from the sensor and it beams outward, and the fraction of the energy returns back to that sensor and it is measured. Okay, so an example of this would be our radar, where we send microwave impulses to measure the size of particulate matter. As I'm sitting here looking at my window, it is snowing. And the radar imagery is showing me that we have ice particles, we have hail, and so that radar has an active sensor that is now beaming that information back. And so radar is an example. LiDAR is another example where we have the sensor attached to a fixed wing airplane or helicopter, and it's sending a laser down to the earth. And that laser beam is bouncing back, and it's providing information regarding treetop. So, for example, the density of the tree canopy, the height of the trees, and so that information will be very helpful at a high resolution, detailed imagery for the LiDAR. Now we can talk about pros and cons of remote sensing. Pros is that it's a fast way for us to get physical patterns. As we see here, we have some infrared wavelengths at the bottom here, and we have some natural wavelengths. Cons are that, when we receive these imageries, we have no scale. There's no graphical names. There's no reference grid. It's just the raw image that's not classified. So, for example, you would have to incorporate other information supporting layers that would help define the cultural boundaries for these imageries. Now we can look at large-scale maps in the example of aerial photography. So remember, large scale shows a small area with lots of details, and aerial photography can be obtained through aircraft, satellites, and other remote sensing platforms. And when you collect this aerial photography or aerial imagery, you have to process it, which is called orthophotography or orthorectification, because you are above the Earth's surface. We know the Earth's surface has this curvature to it, and so you're going to have some distortion that takes place dependent upon the altitude in which you are flying. So we can use many different platforms to collect remotely sensed data. Early remote sensing took place with tying cameras on pigeons, with geographers going up in hot air balloons and taking imagery from afar. But nowadays we use aircraft, we use low, medium, and high altitude. We use higher level spatial details. We also use satellites that can orbit the equator. It can also orbit the poles, and it can maintain at an altitude of about 800 to 900 kilometers. And again, early platforms and instrumentations used was collecting information up in hot air balloons, providing a vertical perspective. As I mentioned, also pigeons were used, and even just climbing up on the highest tower to get an aerial view. So factors of aerial photos, literally when you have a plane flying over a certain area, the type of instrumentation is a gyro-stabilized camera that is focused and fixed over a literal hole in the bottom of the airplane. And so with this stabilization camera, you can get more detailed photos, and you can also point vertically to the ground itself to be directly overhead to try to eliminate some of the distortion that takes place. So we have different remote sensing platforms in the form of airborne sensors and spaceborne sensors itself. Okay, so here's some examples of black and white photography. We define black and white photography as being panchromatic of all colors, and we are defining the wavelengths in the visible part of the electromagnetic spectrum, so 0.4 to 0.7 micrometers in the electromagnetic spectrum. Now, when we look at black and white photography, there's things to think about and perhaps try to eliminate. And so the example would be the atmosphere. A hazy environment or a smoky day would influence the type of scattering that would take place in our wavelength. And so we would probably want to filter out 0.3 to 0.4 of that spectrum, because that's the layer in which we see some of the haze and scattering take place. So the great thing about knowing the different bands into the visible spectrum is that we can eliminate certain bands and combine them to see different combinations. So for example, these are looking at 2 images of the same location. We're looking at bands 1, which is a blue band, and we're looking at band 4, which is going to be a near infrared. So the image on the left, we're looking at, we see a lot of things on this. Band, and we're looking at band 4, which is going to be a near infrared. So the image on the left, we're looking at, we see a lot of things on this map here. I'll let you have some time to look at it. This is an aerial imagery. We see that we have, looks like a road right here. It looks like some farms. Now, notice that we have some interesting features right here. They look like some white cotton balls. So what do you think these guys are? Yeah, so these are going to be clouds. These are going to be some cumulus clouds. Now, there's some features on here that are really hard to see with this particular band. Okay, and this band, so for example, there's a pretty large river right here that it's hard to detect. Now, if we switch our bands, okay, looking at the same imagery, we can look at near infrared imagery, which is going to have a huge player for white bodies and water as a whole. So for example, our river now turns black. Our clouds, as we see here, also turn black as well, because we have some elements of water within the image itself. So we use bands to pull out certain information depending upon what we're looking at. It can be helpful. So around the 1930s, we started to veer from black and white imagery and move to a true color photography. It was more expensive. It required more materials. And so early color images were somewhat poor clarity. We can also see around World War II, special films were developed, which had sensitive to near infrared, near IR wavelengths. And this is going to cover 0.7 to 0.9 of our electromagnetic spectrum. Now, why is near infrared so important? Well, as you can see on this image here, vegetation is easy to depict. So for example, young vegetation really comes to us in the form of red imagery. So for example, if we look at healthy vegetation, which is going to be defined as red, it allows us to see where there's what's invisible to be visible itself. So we can see forestry practices, we can see changes in the health of vegetation when we apply the two together. So this is an example. This is a satellite view of Pike National Forest in Colorado. The satellite view of Copper Mountain Ski Resort in Colorado. Forestry organization and agencies have a unique and critical role in the nation's government, and they serve in public land management, private land regulations, and wildfire management. So while there's significant growth in the roles of the forestry program as a whole, it's important to check in and monitor the overall health of the forest. And so with the use of geospatial technology, the agency can look to see how the forest practices are doing, how the conservation efforts are doing as a whole. Okay, so we can also look at our natural color composites. So these are looking and combining certain bands within the electromagnetic spectrum of 3, 2, and 1. And then we can provide a false color composite, looking at the same imagery and combining the bands, the infrared or the wavelength bands of 4, 3, and 2. Now notice when we do that, the false color composite really allows for us to see the pop of the young vegetation in the bright red, but we also see the water and even the clouds start to pop as a whole.